Okay, so good morning everyone. Um so last class we were discussing how to prove this Subotovskaya's theorem. Okay, so essentially what the theorem states is that, so if we have a function, if we have a Boolean function, and now if we want to consider the formula size of that function, the minimal formula size of that function, then we can give a upper bound, we can give a lower bound on the formula size of the function based on a restriction. Okay. So, let epsilon be some constant. So, we saw that, so R n m, so R superscript and subscript m basically means all restrictions, okay, which leave m variables free. Okay. So, if we are looking at epsilon n, we are looking at all restrictions of n variable functions that will leave epsilon n many or epsilon fraction of the variables as free. Okay. So, the free variables can take any values, the remaining variables are restricted to be either 0 or 1. So, now what this is saying is that if I look at this restricted function, because of course, the restricted function is a smaller function. So, it will have a smaller formula complexity. So, this theorem characterizes the expected formula complexity of that restricted function in terms of the formula complexity of the original function. Okay. And what it says is that it gets restricted by a factor of epsilon to the power 1.5. And we saw last time that showing that it gets restricted by a factor of epsilon is quite trivial, okay, because it is just counting the number of leaves that disappears. So, if we restrict well, if we restrict 1 minus epsilon many variables, then of course, those many leaves of course will get reduced. So, getting epsilon is easy, but the non-trivial part here is how do we get a better upper bound. And the idea that we kind of argued last time that we want to exploit is that we are considering formula over the De Morgan basis. And over the De Morgan basis, what we can argue is that, let us say if I have a AND gate, okay, and let us say one sibling of the AND gate takes a value 0, then irrespective of what the other sibling, I mean what the other subtree looks like, the function evaluates to 0. Okay. For OR gate it is 1. So, we have actually proved this lemma last time, that if we consider a minimal formula for a function, okay, over. So, this is actually over the De Morgan's basis, of course. So, everything that we are discussing now is over the De Morgan's basis. So, if we consider a minimal formula for f, and if we look at any xi leaf, okay, any leaf labeled xi, then if we look at the sibling of that leaf, and if we look at the subtree rooted at that sibling, that cannot have another xi leaf. Okay. So, that cannot have an, well, I should say more precisely, cannot have an xi leaf. Well, if it has an xi, it has to be a leaf only, it cannot be an internal one, but yeah. So, it cannot have xi, and then we argued why this is true, last time we proved. Okay. So, now what we want to prove is that using this lemma, we want to give a restricted version of Subotovskaya's theorem. So, look at this lemma. So, we stated this lemma last time. So, here what we are saying is that if, let us say suppose I have a function with formula complexity greater than 1, okay, and if I restrict just one variable, okay, so one variable gets restricted to some value, remaining n minus 1 variables are free, then the formula, expected formula complexity is at most this 1 minus 1.5 by n of LF. Okay. So, how do we prove this? So, any questions? Okay. So, again, so the proof is not very difficult. I mean, once you have this observation, which we showed last time, the proof kind of is quite obvious. So, let us try to look at the proof. So, what we will do is we will write an expression for this left hand quantity. Okay. So, suppose I have So, what does this mean? So, what this means is that if so the expectation is over some variable, okay, and each variable can take a value 0 or 1. So, basically I can write this as 1 over 2 to the power n sigma I going from 1 to n sigma b taking a value either 0 or 1 that L f has a variable xi that takes a value b. Okay, so, this is just a notation that I am using. Okay. Huh? Which one? This one? No. So, there are it's an average, right. So, expectation means I am taking the average. Okay. So, I am looking at all possible variables xi, and for every variable I am looking at all the values that that variable can take, which is 0 or 1. So, I have a total of 2 n many choices, n variables and 2 values per variable, and I am assigning that value to that particular variable. So, for everything, and I am just looking what is the thing. Okay. So, it is just averaging over all these things. So, now I can rewrite this as, I will write this as L of f minus, okay, is xi is assigned the value b. Sorry. Okay. So, I am just adding and subtracting LF in this expression. Now, what we want to estimate is what is the value of this quantity. Okay, so, let us try to understand what this means. What this means is that if I take the formula for f, okay, and if I take some variable xi and if I give it some value b, then or basically what I would like to estimate is a little more than that. So, this is let us say I and this is over b. So, I would like to estimate actually this entire quantity. So, if I take a variable xi and if I set it to some value b, how much is the decrease in the formula size? Okay, how much is the formula size decreasing? So, any guesses how much? So, let us say forget about b for the timing, let us fix a b. If I assign a value b to a variable xi, how much will the size of the formula decrease by? So, let us give a lower bound. So, at least we want to say how much? At least the number. So, how many such leaves are there? So, we will have at least one xi leaf, right. So, there it will reduce by at least 1. Okay. But can you say a little bit more than that? If I consider this also, if I consider this summation also, so if I look at this particular expression over here, observe that well if I have a xi leaf, okay, whose parent is suppose let us say without loss of generality an AND gate, and if I have some subtree over here, then if xi gets a value 0, okay, then not only this gate can be removed, but any gate over here can be removed as well, right. If this gets a value 1, then only this gate can be removed. So, the point is this expression, okay, so for and if it is an OR, it is the other way around. If it is an OR and you can keep on removing everything, that is fine, but I am just trying to argue that in this part how much can I remove, at this level how much can I remove, okay, because I just want to give a count. Okay, so, here what this is saying is that if we have a structure like this, then for every xi variable, for every xi leaf, for every xi leaf, L of f minus L of f xi getting a value b, and if I sum this over b belonging to 0 1, this is at least equal to 3. At least 3 leaves would get removed, okay. And this is what gives us this 1.5 kind of a thing. 3 leaves basically for one value of xi, I can say that only that leaf will be removed, and for the other value of xi, some leaf over here and some leaf over here, total 3. Okay. So, now let us try to just plug this in back. So, we have this expression over here. So, this expression I can write as being greater than or equal to this. So, I have a minus over here. So, this will be less than or equal to L of f minus 1 over 2n sigma I times 3. Right. Yeah, and it is not just 3, it is actually 3 times Li. Okay. So, for every xi leaf I am removing 3 nodes, for every xi leaf 3 nodes are removed. So, this will be 3 times the number of times xi is present. Okay. For every xi leaf 3 leaves are removed. Okay. So, I will have 3 times Li. So, this I can write as equal to L of f minus 3 over 2n, and sigma Li is nothing but L of f. Okay. So, this is equal to L of f times 1 minus 1.5 by n. Okay. So, this is a, so once we get this observation, this is easy. And where do we use the fact, where do we use this other lemma? Okay, so, let us call this as lemma 2. So, where do we use lemma 2 in this observation? So, we are using lemma 2 as basically to take into account for duplicates, right. So, when I am counting that for every xi leaf 3 leaves are removed, I am using the fact that if I have an xi leaf, here I do not have any other xi leaf, right. So, that is where I am using the lemma. So, this has only some other nodes. Okay. Now, let us come back to the, so this proves lemma 1 over here. Now, let us say I want to use lemma 1 to prove this theorem. Okay. So, one way to prove this theorem would be that I will keep on applying lemma 1 in a iterative manner. Okay. So, I take one variable, I restrict it, I get this bound, and then again I restrict it, and I keep on doing this. So, let us say, so suppose I have f, let me call f as f of n, and then I have f of n minus 1 that I get by restricting one variable, then I have f of n minus 2 and so on. I will have f of m, okay, where m equals epsilon n. Okay. So, this is my sequence of functions that I get by restricting a variable at each step. So, now what I can do is I can apply lemma 1 iteratively, and if I apply lemma 1 iteratively, what I will get is, so basically at some intermediate levels I will get something like this, that well, expectation of sigma in R k minus 1 L f sigma is at most 1 minus 1.5 divided by what would be the denominator. So, the denominator is basically, so here I am restricting from k to k minus 1. So, the denominator is k over here times L of f. Okay. So, f is some k variate function. So, if I keep on doing this again and again, I will get this, but there is one problem with this application, and then basically what I would have is, if I just keep on applying this, I will get 1 minus 1.5 by k whole to the power whatever epsilon n, and that would give me a way to obtain this theorem. But there is one problem in this application. Can you see where it is? Okay. So, this application assumes something. What does it assume? Okay. So, here it assumes that the formula complexity is greater than 1. Now, what can happen is, I mean, one of these intermediate function can have a formula complexity maybe 1, it can also maybe have a formula complexity 0. Okay. I mean, that is possible, right? I mean, we do not know anything about these intermediate formulas. So, I can have a formula here which has a complexity, or I can have a function here which has a formula complexity as 1. So, therefore, this cannot be applied. Okay. So, will not work since lemma 1 assumes that L of f is at least 2. So, now we have to give a generalized version of this lemma. Okay. We have to give a lemma which would basically work for all functions irrespective of their formula size. So, basically that can be taken into account by just introducing a small constant. Okay. So, that is why this 1/3 actually comes. So, we will just introduce some what do I say, some flexibility when we give the bound. So, let me state another lemma, which is we have 2 here. So, let me call this as lemma 3. So, what we will prove is that expectation sigma in R n n minus 1 of L of f sigma minus 1/3 is at most 1 minus 1.5 by n L of f. I think one second, let me just verify this. Okay, yeah, L of f minus 1/3. Okay, and this is for all functions. or even for all formula sizes. So, how do we observe this? So, we will just show it in 3 cases. Case 1 is when L of f is greater than 1, then case 2 is when L of f is equal to 1, and case 3 is when L of f is equal to 0. Okay, so, let us look at the 3 cases. So, proof. So, if L of f is greater than 1. So, let us try to see what happens over here. So, the left hand side is expected value L of f sigma. Now, this is difference of 2 quantities. So, I can write this as L of f sigma. I can take the 1/3 minus I can take the 1/3 outside the expectation is less than or equal to what is this quantity. So, by lemma 1 we know that if L of f is greater than 1, this quantity is bounded by that L of f into 1 minus 1.5 over n, right. So, this is L of f into 1 minus 1.5 over n, and I have a minus 1/3. Okay. Now, what do I want? I just want to bring this 1/3 over here. So, that is quite easy. So, this I can write as less than or equal to L of f 1 minus 1.5. You want to turn the fan? I think the regulator, yeah, 1.5 over n. So, this is I will just introduce some additional terms over here. So, what do I want to introduce? So, I have a minus 1/3 and I will introduce a, so this times this. So, this is 3 by 2 of n. So, plus 1/3 dot 3 by 2n. So, observe that this is a positive quantity, right. So, n is positive. So, this entire quantity is positive. So, this is greater than or equal to this, but doing this kind of will give me that this is equal to L of f minus 1/3. Okay. Just a small modification. Now, what happens if L of f equals 1? So, if L of f equals 1, let us look at both the left hand side and the right hand side of this expression. So, what does the left hand side evaluate to? So, if L of f equals 1, I mean I can again once again write this as expected value L of minus 1/3. What is the value? So, what does this evaluate to? Just think for a moment. What are we saying here? That L of f is 1, which means that I have a function which has only one leaf, for which there is a formula which has only one leaf, and that leaf is labeled by some variable. It can be any one of the variables. So, what does this mean? It means that, well, if I assign some value to that variable, only then the size of the formula decreases. If I assign value to some other variable, the size of the formula remains the same. Okay. And I am looking at the expectation. So, the probability that I pick that particular variable is 1 over n. Okay. So, if I pick that particular variable, so this expectation is basically 1 over n. If I pick that particular variable, the size becomes 0, and for all the other variables, so 1 minus 1 over n, the size remains 1. Okay. minus 1/3. So, this is 1 minus 1 over n minus 1/3 is 2/3 minus 1 over n, right. Now, what about the RHS? RHS is well, we know that L of f is equal to 1. So, 1 minus 1/3 is 2/3, 2/3 into this quantity is equal to 2/3 into 1 is 2 by 3 minus 2/3 into 3 by 2 of n is nothing but 1 over n. So, LHS is equal to RHS over here. Okay. So, here you kind of see why we picked 1/3. What is the role of 1/3 over here? I mean, why did suddenly we have this constant 1/3 appearing? Okay, you can actually pick some other, I mean, even for some other constant also it would work, but for 1/3 they are kind of becoming the same. And I will just leave the other one. The last case is when L of f is equal to 0. You can actually again verify that in this case also LHS will be less than RHS. Okay. So, if L of f is equal to 0, this side becomes minus 1/3 into this quantity. So, this is basically between 0 and minus 1/3, this RHS will turn out to be, and left hand side will be so the expected size would be, so this is 0 because L of f is 0. So, even restricting it becomes 0. So, this is 0 minus 1/3. So, 1/3. So, LHS is 1/3, RHS will be something between minus 1/3 and 0. So, RHS is greater than LHS. Okay. So, that completes the proof of lemma 3. So, now we are in a position to use lemma 3 to prove our main theorem. Okay. So, how do we prove the main result? So, what we have over here is, as I said, for any arbitrary k, okay, fine. What we have is if I look at a sigma and if I restrict from, let us say, k plus 1 to k, okay, L of f sigma minus 1/3 is at most 1 minus 1.5, yeah, we have a k plus 1 times L of f minus 1/3. So, I am assuming this is correct. Yeah, okay. So, basically what I am saying is consider an f, okay, which is already restricted to k plus 1 variable. Okay. So, I will basically I am doing it iteratively. So, first I start with n, then I, let us say I come to a level when it is restricted to k plus 1 variable, and now I want to restrict it to one more variable, I want to restrict it down to k. Okay. So, f sigma is basically a function which is restricted to k variable. Then by lemma 3 we have this observation. Okay. So, this is a direct application of lemma 3, and I can also write an expectation term over here. I mean, I can write this as E of L of f minus 1/3. I mean, there is no, I mean, yeah, so there is no probability over here. So, this is kind of like the same value. Okay. So, okay, and So, now if I do this how many times? So, I have to bring it down to epsilon n. Okay. So, if I do this many times, what I will get is expectation sigma r n epsilon n is in fact, let me just, so this should not be f over here, this should be f k plus 1. Okay. 1 second, let me. Sigma r n epsilon n L f sigma minus 1/3 will be how much times the value of L of f minus 1/3. So, how many times do I have to apply this? So, it will be 1, in fact, it will be a product over here each time I apply this. So, product of k going from m plus 1 to n 1 minus 1.5 by k, right. So, every time I do this I am adding a additional multiplicative factor of this quantity. Okay. Now, what does this evaluate to? So, this actually again it is easy to see that yeah, and so yeah, I mean I think I wrote somewhere over here that yeah, m is nothing but epsilon n. Okay. So, in fact, I can write here also instead of epsilon n, let me just use m over here, okay, because I am using m over here as well. Okay. So, this quantity, what does this evaluate to? Okay. So, I will use the inequality 1 minus x is, so what kind of inequality do I need to use over here? Okay. So, I have some products, okay, and I want to bound these product by some function of n and m. Okay. So, basically what I would use is the inequality 1 minus x is less than e to the power minus x, okay, for x between 0 and 1. So, this follows from Taylor's expansion. So, these are the first two terms of the Taylor expansion of e to the power minus f, everything else can be shown to be positive. So, therefore, this turns out to be, so this quantity over here becomes less than or equal to e to the power minus 1.5 by k, and because it is in the exponent now, this is summed over k going from m plus 1 to n. So, I take the minus 1.5 outside. So, e to the power minus 1.5 sigma 1 over k, k going from m plus 1 to n. So, what does this turn out to be? So, note that this I can write this as sigma n minus sigma m, of 1 over k. And what is e to the power sigma 1 over k? Okay. So, sigma 1 over k can be, I mean, one upper bound on sigma 1 over k is that it is ln of n, right. So, I will just use the inequality, okay, e to the power sigma 1 over k going up to n minus sigma 1 over k going up to m whole to the power minus 1.5 L of f minus 1/3. So, this quantity is upper bounded by ln of n. So, this would become e to the power ln n minus e to the power ln m is e to the power ln of n by m, okay, whole to the power minus 1.5 minus 1/3. So, taking the minus inside, I will have m over n. So, this becomes equal to m by n to the power 1.5. Okay. Now, what is m by n? So, m is epsilon times n. So, this is epsilon to the power 1.5. Okay. So, are we done? So, we are not quite done, because here I have a minus 1/3 term and I want to take that outside. So, this is this 1/3 term I can drop, because I just need a upper bound over here and this is only reducing. So, this is less than or equal to epsilon to the power 1.5 into L of f. Okay. So, L of f minus 1/3 is smaller than L of f, and now this is this 1/3 I can take outside the expectation. So, what I get is, okay, let me just write it over here. I get is expectation of sigma L of f sigma is less than or equal to epsilon to the power 1.5 L of f plus 1/3. Okay. So, I bring this 1/3 on the right hand side, and that gives us the theorem. Okay. Okay. So, any questions? So, let us look at a very quick application of this theorem. So, where we can apply. So, once again let us consider the Zor function, okay, or the parity function. So, parity function is also known as the Zor function. So, Zor n of x1 up to xn is basically x1 parity up to xn. Okay. So, how can we give a lower bound on this function? Okay. So, let f be the Zor function, and now to give a lower bound I have to choose an epsilon, because if I want to apply this theorem on some function, of course, firstly I choose the function to be whatever it is, and then I have to choose an epsilon. Okay. Only then can I apply this bound. Okay. So, what epsilon do I want to choose? Okay. So, note that the smaller the value of epsilon is, the lesser is the number of free variables, right. So, if epsilon is very small, then I have very small number of free variables that are left. Now, how do you think, I mean, how do you proceed? So, let us say I give you some function and I ask you to prove a lower bound using this theorem, or you want to think, how would you proceed? So, look at this function parity. So, how many variables do you need for parity to change its value? So, let us say if I restrict parity to some from n to some m many variables, how large should m be, so that the value of parity depends, or the value of XOR depends on that many number of variables. So, irrespective of what I restrict the other n minus m variables to be, these m variables should determine the value of XOR. For what value of m is that true? Any guesses? 1, why 1? Exactly. So, irrespective, so look at this function. So, let us say I fix the value of x 1 up to x of n minus 1 to be something 0, 1, whatever, something. Now, the value of parity irrespective of that will depend on the value of x n. Okay. So, if x n gets some value, parity will get some value, and for x n to be the other value, parity will be the other value. Right. So, I can fix any one of them. So, that is the idea that I want to use. So, I will choose an epsilon which kind of fixes n minus 1 variables and only one variable remains. Okay. So, I will choose epsilon to be what? One over n. Okay. So, if epsilon is chosen as 1 over n, then m becomes 1. So, only one variable is free. So, then what is this quantity? Expected value of sigma chosen from R n, epsilon n is now 1, L of f sigma. What is this quantity? So, here note that all variables except one variable is fixed, only one variable is free. How large will be the formula size, or at least how large is it? Can you give a lower bound on this? Can it be 0, the formula size? See the you can the entire function depends on that one variable. Now, you have only one variable and the function depends on that. Okay, so, the size of the formula cannot be 0. Okay. So, it has to depend, I mean that variable has to be present in this formula, right. So, this quantity is actually, well, at least 1 over here. Okay. In fact, it is exactly equal to 1. Okay. So, we have this, and now we will just apply this theorem over here. So, this is greater than or equal to 1, and combining with Subotovskaya's theorem. So, by what we have is 1 is at most epsilon to the power 1.5 times L of XOR n plus 1/3. So, now just rearranging, what I get is L of XOR n is greater than or equal to, what was my epsilon? Epsilon was 1 by n. So, this is greater than or equal to n to the power 1.5, or let me just write it as omega this. Okay. Now, is this the best that we have? Why not? Kravchenko's theorem has already given us a lower bound of n squared, right. So, this is a weaker lower bound that we are getting, right. But that is okay. I mean, I just wanted to show an application. So, Kravchenko's theorem of course gives us a better lower bound, not only is it a better lower bound, one can actually show that there exist formulas which meet that lower bound, where one can construct a formula of size n square. So, that is actually a tight lower bound. Okay. So, this is not the best one, but this is just the way in which this theorem can be applied. Okay. So, any questions? Yes, there are, you can have such lower bounds for other functions as well. Okay. Other bases, yeah. So, the thing, so you see where the crux of this theorem lies in. The crux of this theorem lies in that analysis, that if you have an AND or a OR gate, then if I have a xi leaf on one side of that gate, the other side will not have an xi leaf. That is kind of the crux of this theorem, right, because you use that theorem to show that the size of this, if I look at any fixed variable and if I look at both the values of that variable, it basically the size of the function. So, if I fix that variable, the resultant formula reduces by at least 3 for every occurrence of that variable. If that variable occurs Li times, it reduces by a factor of at least 3 times Li. So, that is kind of the crux. Now, how can you make such a statement for some other gates? Okay, that is not clear. For AND and OR, it works because the very property of AND and OR gives us that, well, it depends only on one variable for some value. So, it is very specific to De Morgan spaces. So, everything else is kind of just putting things in place, but that is the essential crux of this entire theorem. Any other questions?
So, when will it be 0?
Which one?
The expected value of size of formula.
The expected value, when will it be 0? So, the expected value will be 0 when that formula takes, I mean when that function has a formula of size 0 for all possible restrictions, right? Huh? Which one should be constant? Exactly, yeah, it has to take, I mean, see, you can have functions which do not depend on any variable, right? You can have a constant function. So, what can happen is, maybe for some other function, some function, if I restrict it to maybe half the number of bits, the remaining half bits kind of are irrelevant. The function anyway goes to some constant 0 or 1. In that case, the expected size will be 0 for such a restriction, but that those are, I do not know. So, those are very probably restrictive functions, I mean, which in some sense you are saying that it does not depend on half the number of variables or something like that. But parity is one function which depends on each and every bit in some sense. I mean, even if I restrict n minus 1 bits and 1 bit is free, that can decide the value of parity. So, everything boils down to understanding how much do I restrict a function, that how much is taken care of by this epsilon term, okay, and after I restrict by that much, what does the resultant formula look like. Okay. So, here what we know is that if I restrict it by this much quantity, the resultant formula will still have at least one gate, it has to have that one gate. That is why I get this plus greater than equal to 1 bound over here. Okay. So, now I will talk about another function, okay, called the Andreev function. Okay. So, why we want to discuss this function will be clear in a moment. So, we will try to give a, we will discuss this function and we will try to give a lower bound on this function using this theorem, and it can easily be shown that that lower bound and kind of matches the upper bound for that function as well. Okay. And this function will actually again occur, I mean later on in the course as well. Okay. So, this is a important function. So, what is this function? So, the Andreev function is written as a n. Okay. So, it is a n and it depends on two inputs x and y. Okay. And x comma y are bit strings of length n. Okay. So, you can think of this function as being a map from 0 1 to the power n cross 0 1 to the power n, and it would output a single bit. So, this is not exactly a Boolean function, but we will see what we can do over here. Okay. So, how is this function defined? So, the way this function is defined is as follows. I will give a pictorial view, and that is the best way to understand this is take the variable x or take the string x. So, what we will do is I will divide the string x into n by log n, okay, or I will divide the string x into log n chunks of n by log n bits each. Okay. So, I will have log n many rows and n by log n many columns. Okay. So, this is my variable x. Okay. So, you can think of it this way, that the first n by log n bits is in the first row, the next n by log n bits is in the second row, and so on, and the last n by log n bits is in the last row. Now, what I will do is I will take a XOR of all the bits in a particular row. Okay. So, for each row I will take a XOR of all the bits. Okay. So, XOR of all the n by log n bits. What does that give us? Let us say that gives us some string let us call it as z, and the length of this string is log n, right. Now, what I will do is, so z, where size of z is log n. Okay. Now, what I will do is I will use z to index the string y. Okay. So, I have this string y also, okay, and I will use z to index a bit in y, and this is the output of the function. Clear? Because any string of length n can be indexed by a string of length log n. Okay. So, whatever that value is, whatever the value of z is in decimal, I will use it to index it, and that is my value. Okay. So, clear what the function is? So, now what do I want to do? So, any confusion? Z has log n bits, yes. So, let us look at an example. So, suppose z is the string 101. So, what is 101 in decimal? It is 5, right. So, it will look at the fifth position of y. If z is let us say 1 1 1, then it is equal to 7. So, it will look at the seventh position, right. So, basically if z is let us say a 3-bit string, then it can index a string up to length 8. So, that is the idea, and whatever that value is, whatever the value at that position is, that is the output. So, now any string of length n can be thought of as a function on log n, assume n is a power of 2 here. So, can be thought of as a function, can be thought of as a Boolean function, not just a function, as a Boolean function on log n variables. How do you think of a string as a function? How do you think? Huh? Exactly. So, essentially what you are saying is that this is kind of the truth table of that function. So, if I have a function on log n variables, the size of the truth table is 2 to the power log n, which is n. Okay. So, this string is essentially the kind of represents what the output of that function is for each choice of those log n many variables. Okay. So, the string here is the truth table of the function. So, this is kind of like a equivalent way. Okay. So, any function on n variables is essentially a string of length 2 to the power n, and any string of length 2 to the power n is a function on n variables. So, these are two equivalent ways of looking at the same thing, and this only whatever I am saying is for Boolean functions, right, because yeah, for obvious reasons. Okay. So, now what we will do is we will use the following. So, recall this theorem, Riordan-Shannon's theorem. Okay. So, what was Riordan-Shannon's theorem? So, let me just recall it for you. So, Riordan-Shannon's theorem gave us a lower bound on the formula size of any function, okay, over any arbitrary basis. So, it was based on, so Shannon's theorem was for lower bound on the circuit size, and Riordan-Shannon was lower bound on the formula size. Okay. So, essentially what it says is that if I look at any function f, okay, on n variables, then or it kind of said a little more, it said that for most functions on n variable, the formula size is at least 2 to the power n divided by log n. Okay. So, there was a delta also, but we can choose delta to be anything that we want. So, here now I have a function on log n variable. So, what I can say is that by Riordan-Shannon's theorem, there exists a function f on log n variables such that L of f is at least, so 2 to the power log n is n by log of log n is log n. So, we know that there is a function on log n variables for which the complexity, the formula complexity is at least this much. Okay. Now, what I will do is, I have this function. Now, I said that I can think of functions and strings equivalently. Okay. So, look at the corresponding string of length, how much? n, right. So, if I have function on log n variables, its truth table is of size 2 to the power log n, which is n. Okay. So, let y star be the corresponding string, or the string corresponding to f over here. Okay. Of course, this is obvious, but yeah. Now, what I will do is I will just define another function, I think. Yeah. So, I will define another function let. So, I had the function Andreev function a n, which took 2 bits as input. So, now I will define another function a n star, and this is a Boolean function now. This is a function on one string of n variables, which is equal to a n of x on this fixed string y star. Okay. So, what are we trying to do? Okay, what is the intuition? Okay, so, instead of looking at it mechanically, let us try to understand. So, what we are trying to do is using, so we have the Andreev function. Okay. Now, for the Andreev function, I am trying to choose a argument for the second part, okay, which makes it most complex. Okay. So, y star is kind of a string which has very large formula complexity, of this much. So, that is the y star that I choose. So, I fix that as my y star, and now I look at this. Now, what can I say about the formula complexity of a n star, or what can I say about the formula complexity of a n? So, L of a n, and if I look at L of a n star, how do these two compare? So, I want to give, so my goal is to give a lower bound on the formula complexity of a n. Okay. So, that was what my initial goal was. So, I considered a function and I want to consider a lower bound on this formula complexity of this. Now, I have come to another function, I have defined another function a n star. How do these two lower bounds compare? Which should be more? A n, why? Exactly. So, this is a restricted function. So, this is nothing but a restriction of a n, right, and we saw that any restriction has a lower formula. That is for obvious reasons, that here I have 2 n bits, here I have n bits. Okay. So, this is clearly well greater than or equal to this. So, in other words, if I am able to give a lower bound for a n star on the formula size of a n star, I will get a lower bound for a n as well. So, from now on I will only focus on this function. Okay. Okay. So, let me write this. So, lower bound for a n star implies a lower bound for a n. Now, how can I get a lower bound for a n star? So, let us understand the function a n star. Okay. So, anything else? Okay. So, what we will prove is that L of a n star is omega n to the power 2.5 minus small o of 1. Okay. So, we will show that it has a formula complexity of at least n to the power 2.5 minus some small, but we will see what those are. So, yeah, so this will I think take some time. So, I think I will end over here because this will take a little time. So, we will continue this next time. In the meantime, you can actually think how one can design a lower bound for A n star using this Subatovskaya's theorem, but we will come back to this next lecture. Okay, thank you.